Ladies and gentlemen, today we're going to be talking about classifying numbers and then reviewing some basic algebra, like simplifying expressions, working with some variables. I'm going to go through the terminology and definitions of classifying numbers in the technical terms and give you a few examples as well. I've also posted these notes on Google Classroom already, and this video will be up as well. So when we think of natural numbers, okay, natural numbers are what we call counting numbers. So when you think of counting, you usually start with 1, 2, 3. You don't start with 0 when you start counting, and you don't normally count by halves. So counting numbers we considered natural numbers. Whole numbers are our counting numbers in addition to so there are counting numbers and 0. So it's 0, 1, 2, 3, etc. So again, whole numbers include our natural numbers or our counting numbers. So I'll actually write that as natural numbers so that you know. And our counting numbers. And 0. Integers include our natural numbers, our whole numbers, and negative whole numbers. So here we will go like -2, -1, 0, 1, 2, 3, etc. Our rational numbers in its simplest form are numbers that can be turned into a simple fraction. So just numbers that can be turned into a fraction. So this would include integers, whole numbers, and natural numbers, as well as repeating decimals. So giving a few examples of rational numbers, we have like 4, 1/2, -1/0.33 repeating, and then 0.7 and 5. Irrational numbers, again in simplest terms, are numbers that cannot be turned into a simple fraction. So giving examples of those irrational numbers, the most basic and best example I could give would be pi. Pi is the best example of an irrational number. And then like square root of 2, square root of 7, and then let's say we did square root of 2/3. If you want to get a little bit more technical with the irrational numbers, there are numbers, integers, where they're decimal representations. So integers where they're decimal representations, or numbers where they're decimal representations, neither terminate nor repeat. Ran out of space a little bit, but I wanted to make sure you all could read what I wrote. And then real numbers are pretty much all of the above. And again, all of the above. And then imaginary numbers. Imaginary numbers are non-real numbers. Again, that symbol before it was a hashtag was a pound symbol or the symbol for numbers. So these are square roots of negative numbers. So I'll give an example. We got 3i square root of a negative 7, or I square root of 3. So using these examples, you'll commonly see a diagram. It kind of lays out how this stuff looks, and I'll plug in some examples. We'll start off with the most recent one that we just did, which is imaginary numbers. So I have 3i, I have I square root of 2, square root of a negative 5. Sorry, it's a little raggedy square root symbol. Negative 4, I. All of these are examples of imaginary numbers where you were trying to take a square root of a negative number. Irrational numbers, the best examples that we can give would be pi, or let's say the square root of 5, because when you take the square root of 5, it's a repeating number that neither terminates, it's a number that when you take the square root, it does not terminate, nor does it repeat. Sorry. When we look at natural numbers, again, those are your counting numbers. So you're going to have 1 is an example, 100, 2, 25, 33, just numbers that we use to count with. Whole numbers are going to be our natural numbers plus the number 0. So it'll be like 0, 7, and 3 are solid examples of whole numbers. And then integers are going to be your whole numbers and your natural numbers plus negatives. So if we put in like a negative 5 as an example, or a negative 2 as an example, 0, 10, all of these are considered integers. And then the last set of numbers before we get into the big category of real numbers are rational numbers, or numbers that you can convert to a simple fraction. So I've got 3/4, 0.5, negative 6, any repeating decimal, so 0.33 repeating, which is 1/3. And then if you look at the way that this diagram is set up, real numbers are everything in this box. So irrational numbers, natural, whole numbers, integers, and rational numbers. And then if you look at these circles, our whole numbers include the natural numbers. So if it's inside of another circle, that means that that category includes the other one. So whole numbers includes natural numbers, and it adds 0 to it. Integers includes whole numbers, natural numbers, and negative numbers. And irrational numbers includes integers, whole numbers, natural numbers, and it adds in any decimals or repeating decimals that can be represented as simple decimals, not decimals, simple fractions. And then real numbers includes all of this stuff. So basically, if anything's a rational, integer, whole number, natural number, or irrational number, it's a real number. And then imaginary is just kind of the red-headed stepchild off to the side. So we're going to go through a few examples where we're actually classifying. And I'm going to zoom out a bit just so that we can actually have our charts next to the examples that we're doing to make it a little bit easier. So for number 13, again, it is a natural number. We would count with the number 13. It's also a whole number. And this is asking us to classify each number, list all categories that it falls into. It's an integer. It's a rational number because we can convert it to a simple fraction. If I wrote it as 13 over 1. And since it falls into all 4 of these categories, it's also considered a real number as well. So it falls into all of those categories. If we look at example 1b, we have 1/2. So we know that this one is a rational number. It's not a counting number. We don't normally count by halves. It's not a whole number because it's not 0 or a counting number. It's not an integer because it's actually a decimal. And then the only thing it could be is a rational number. We know it's not imaginary because we're not taking the square root of a negative number, and you don't see an I. And since it's rational, it's also real. So just a good little note, if it falls into any of these categories of whole, natural, integers, rational, irrational, it's also real. And then we look at number 4. We wouldn't count with a -4. It's not considered a whole number because whole numbers don't include negative numbers. It is an integer because integer includes negative whole numbers. It's a rational number because we can convert that to a simple fraction rather easily, is a -4/1. And since it falls into these two categories, that also makes it a real number. If we look at D, we can convert this to a simple fraction. So it'll be a rational number. It's not an integer because it's a decimal. And since it's a rational number, then it naturally falls into the category of a real number. Pi, I mentioned that earlier. This is the best example, most popular example of an irrational number. And since it's irrational, it's also a real number. And then last but not least, we have 2i. Since we're dealing with an I, that makes it an imaginary number. Again, this symbol, before it was a hashtag, is a pound symbol, which stands for a number. We've been doing a lot with equations and expressions lately and simplifying those. And most recently we were working with slope. One of the things that came up was when we were dealing with a perpendicular slope, which meant that we were dealing with the opposite reciprocal. So those terms came back. And here it says the opposite or additive inverse of any number, A. So when we think of this, an example would be -4, -8 is, and in this particular case, a -A. Whenever we're talking about the opposite, we're generally saying that we're going to change or switch the sign, which applies to positive or negative. So if I switch the sign to these, this will be a +4 and this will be a +8. If they started off as a positive, they would be a negative. In this case, I gave you negative examples and they would switch to positive. Here is the reciprocal or multiplicative inverse of any number A is, it's going to be 1/A, which is where you flip your fraction. The numerator becomes the denominator and the denominator becomes the numerator. You just flip your fractions. So you can either have a question or you can be asked to find the opposite or the reciprocal or both. And you know that if they're asking for opposite, all you do is change the sign. If they're asking for reciprocal, you flip the fraction. So here's a few examples where we're working through of using opposites and reciprocals. So here they said find the opposite and reciprocal of each number. So we got the opposite and reciprocal, so I know what we're looking for. So again, opposite, all we're doing is changing the sign. So this becomes a -4 1/5. And then reciprocal, I can't just find the reciprocal if I'm not dealing with the fraction. So since I have my number the way it is with a whole number and a partial whole number, I need to convert that to an improper fraction instead of like having the extra over here. So the way I like to do it is a -4, and then you have the 1/5 multiply the -4 times 5, which will get you 20, and then add 1. So my fraction would be, actually this will be a positive because my original one was a positive. 4 times 5, which is 20, plus 1 is 21 over 5. So if I represented this as a fraction, it's 21 over 5. And then reciprocal means that I flip it, so this will be 5 over 21. So again, if I want to take this and convert it to an improper fraction, let me zoom in a bit since we don't need that chart anymore. I'm going to multiply the whole number times the denominator. 4 times 5 gave me 20, and then I add the numerator, and that's how I got 21 over 5. And since we're looking for the reciprocal, I'm going to flip it. For B, this is in the tenths, hundredths, thousandths place. So I can rewrite this as an opposite. All I do is just switch the sign. So this becomes a positive 0.002. But again, if I'm trying to find the reciprocal, I need to be able to get this into a fraction. If I rewrote this as a fraction, I would get 2, or in this case a -2 over 1,000. And if I flip that, it'll be a -1,000 over 2, which is a -500. Also put boxes around so I don't have to go looking for stuff. And then this last one is a little bit easier. If we want to try and find the opposite of this one, again opposite, all I do is just switch the sign. So this becomes a positive 4 over 9, and then the reciprocal, you have to flip the fraction. So it stays a negative, and then it's a 9 over 4. Opposite means change the sign, reciprocal means flip the fraction. Next, for example 3, this is where we're going to put some of the stuff that we're learning into practice. So whenever you're evaluating an expression and they give you a number for your variable, you just plug it in everywhere that you see your variable. So I'm going to plug in my 6 here and here, and then I'm going to use PEMDAS to evaluate my expression. So here I have a 6 minus 18 squared minus 4 times 6. Parentheses goes first, so 6 minus 12 is a -12 squared minus 4 times 6, which is 24. -12 squared gives me a positive 144 minus 24, which equals 120. So I did my parentheses, then my exponent, and then I did my subtraction, which comes a little bit later down the line in my PEMDAS. I have another example. They gave us our variables. So the K's, I'm going to plug in everywhere that I see a K. And then my N's, I'm going to plug in everywhere that I see an N. So if I rewrite this, I have a -1. Put that in parentheses. Every time I plug something in, I put it in parentheses. I'm going to use a different color just for sake of keeping everything that I plugged in separate. Minus 3, put that in parentheses. And then again, my K was a -1. Then minus 5. And then for my N, I'm plugging in a negative 2, close my parentheses, and then plus 4, and again plugging in for my n, it's going to be a negative 2, and we go back to PEMDAS. I'm just going to handle this one right off the bat just because I know that a negative 1 squared is a positive 1, and it's going to be minus, and then on the inside I have to handle my multiplication first. 3 times a negative 1 is a negative 3, and then plus negative 5 times a negative 2, or a negative or minus times a negative is a plus 10, and then plus 4 times a negative 2, which is a negative 8. So I have 1, and then negative 3 plus 10 is going to be minus 7, because negative 3 plus 10 is a positive 7, and then there's a minus right there, and then minus 8. So 1 minus 7 is a negative 6, minus 8 is a negative 14. You could have also distributed that minus 1 to both of your terms and gotten 1 plus 3 minus 10, which is 1 plus 3 is 14, minus 10 is a negative 6, and then subtracted 8, and you would have still gotten a negative 14. Here we're looking at this in like a word problem style situation. It says the expression negative 0.3y plus 61 models the percent of eligible voters who voted in presidential elections from 1960 to 2000, where y represents the number of years after 1960. Find the approximate number of voters who voted in 1988. So we know that y is the number of years, and we're looking for the approximate number of voters in 1988. So we have to find how many years passed from 1988 to 1960, which is 28 years, which is our y. So then we plug that in. I've got a negative 0.3. I'm going to plug in my 28 plus 61. I'm going to get out my calculator just to make it a little bit easier because I'm dealing with decimals. And I also want to show you all that when you plug in, you want to make sure that you put things in parentheses, because sometimes your calculator can be a little dumb. So you got a negative 0.3, the 0, you can put it in there or not, open parentheses 28, close parentheses, plus 61. When you push enter, you get 52.6%. 52.6%. So all I did was take what they gave me, the equation, figure out what my y was, which was my input in this particular case, and find my output, which is 52.16. And then we got a few more examples of practicing simplifying expressions. And again, all of this we're dealing with PEMDAS. Don't forget about PEMDAS, parentheses, exponents, multiplication, division, addition, and subtraction. And we usually use it going this way when we're simplifying expressions. So I have parentheses in my first one, so I got to take care of that first. So 2 plus 1 is 3. So I've got 4 plus 3 squared. 3 squared is 9. So 4 plus 9 equals 13. Put a box around it so that we don't have to go searching. B looks a little tricky, but I like to think about it as, hey, we start from the inside of our parentheses if we're using PEMDAS, and then work our way outside from there. So if we start from the inside, I've got 4 plus 3, and then 4 minus 2, and then 6 minus 3 is 3, and then close our bracket, and then all of that is going to be divided by 2, and then 2 times 3 is 6, doing this part right here, 4 plus 3, open bracket, 4 minus 6, close bracket, divided by 2, and then we're still staying inside of the brackets, which is serving as parentheses in this case. 4 minus 6, so 4 plus 3, 4 minus 6 is 2, divided by 2. So I took care of this part next, and then here we're getting into the rest of our PEMDAS. Multiplication comes before division, so I need to multiply these. I'm just going to put a little arrow up here because I'm running out of space. So I've got 4, 3 times 2 is plus 6, divided by 2. Next is division. So I have to divide these two. 6 divided by 2 is 3. So 4 plus 3, addition, equals 7. Let me put a box around it. And I'm sorry, I made a mistake. This should actually be 4 minus 2 is a negative 2, which means that 3 times a negative 2 will change this to a minus 6. Everyone knows I make mistakes. So negative 6 divided by 3 would actually be a negative 3. So it's a negative. Here's another negative. So 4 minus 3, my answer should actually be 1. Sorry for the confusion. Let's look at another example, which is C. I'll try not to make any mistakes this time. Don't hold me to that. So the first thing we do is we look at PEMDAS. I have parentheses, so I need to take care of my parentheses first. So you can either distribute, and in this case it's really all we can do, because this has an H and this has a K. We can't exactly combine those like terms. So my first step is going to be to distribute my 7. So this is 2H minus 3K plus 14H minus 21K. Keep in mind, I see mistakes all the time where people only distribute to the first term. You need to make sure that you multiply times both terms. And then you have to combine your like terms. So I have a 2H here, and then a plus 14H there. And then I have a minus 3K and a minus 21K. I group my terms by identifying which ones are like. So I've got 2H plus 14H is 16H, and then minus 3K minus 21K is a minus 21K. I'll put a box around it. These are a little bit easier. These are a little bit easier. We don't have to do any distribution. All this one is doing is combining like terms. I like to use different colors. So I got a 5x squared, and then I got a 5x squared here, an x squared here. Notice that I took the sign in front of that term and the term. I can't combine an x and an x to the second because they have to have the same variable and the same exponent, same variables if it has more than one, or it has to be a constant in order to combine terms that are like. So in this case I've got x to the second and x to the second. So this becomes 6x to the second because all I do is add the coefficients, and there's an understood 1 in front of this x squared, and then minus 3x. And we put a box around it. That's it. So all I did was combine like terms there. move up to where it says solve each equation. And we're going to use those same principles that we used before. So for number 5, our first step is to distribute. Again, I apologize for my handwriting. It hasn't progressed since probably about the first grade. I'm going to distribute my 2 to both of my terms. So I've got 2y minus 8 plus 6 equals 70. Then I need to combine my like terms. So I've got a minus 8 and a 6. Those are my two constants. So I'm going to combine those. So I've got 2y minus 2 equals 72. I'm trying to get my variable by itself. I'm trying to isolate my variable. So I've got to get rid of that 2. The opposite of subtraction, to undo subtraction, is addition. So I'm going to add 2 to both sides. And I do this sometimes. This was 70. And I think about the next step. So 70 plus 2 is 72. 2y is equal to 72. Again, that 2y is the same thing as saying 2 times y. And the opposite of multiplication is division. So I'm going to divide both sides by 2. And y equals 36. Easy. As my son says, easy peasy, lemon squeezy. Five B is just like 5A, except I have to distribute on both sides. So I'm going to distribute my 6 and I'm going to distribute my 2. So 6 times t is 6t minus 2. So 6 times a minus or negative 2 is 12, is equal to 2 times 9, which is 18, minus 2t. So 2 times 2 is 4, and that's going to be a minus 4t. And now I have to isolate my variables in order to solve. I usually like to deal with positive variables whenever possible, or coefficients in front of my variables. So I'm going to add 4t to both sides. Now notice where I put my 4t. I put my 4t underneath the 6t because they're like terms. Don't put it underneath the minus 12, because I see kids all the time that combine the 12 with the 4, and then you end up messing the whole problem up. So this becomes 10t. I bring down my 12 is equal to 18. And now I got to get my variable by itself, so I need to move this minus 12. The opposite of subtraction is addition. So I'm going to add 12 to both sides. And I've got 10t is equal to 30. And again, this 10t is the same thing as saying 10 times t. Make sure you all can see it. So to undo multiplication, I'm going to divide by 10, and I get t equals 3. So for example 6, we don't have very many numbers. All we're going to do is just manipulate our equations to solve for the given variable. So here we're looking for h, and here we're looking for r. I'm going to rewrite it just so it's a little bit bigger. The h. So I like to get rid of the coefficients first whenever possible. If I have an equation like this, which can actually be written as b times h over 2. It's the same thing. So to get rid of this 1/2, I'm going to multiply both sides by 2. So I get 2a is equal to bh. And then there's an understood multiplication symbol underneath that. In between those two variables. So I'm going to get rid of the b by undoing that, divide both sides by b, and I get h equals 2a over b. And I put a box around it. I solve my equation in terms of a variable. And if we look at S is even easier. I'm going to rewrite it to make it a little bit bigger. 2 pi RH. I'm trying to solve for R. And there's an understood multiplication symbol between each of these numbers and variables. I can actually undo all of those at one time by dividing this side by everything that I'm multiplying to get rid of it. So I'm going to divide by 2, I'm going to divide by pi, and I'm going to divide by h on both sides. And I get R is equal to S divided by 2 pi h. If you have any questions, feel free to comment, like, subscribe if it works, or shoot me an email or message if you're one of my students on Google Classroom, and let me know what you think.